Welcome to Algorithm video series. Today in this tutorial we'll talk about lower bound and upper bound problems. Also we'll find the count of occurrence of the target element using lower bound and upper bound index. So first we'll talk about lower bound problem. Here is the problem statement. Given a sorted list and a target value, find the index of the first element that is greater than or equal to the target. If no such element exists, return size of the list. Here input is a sorted list which can contain duplicate elements and a target value. Output is first position where we can fit target. That is, we want first position where element is greater than or equal to target element. For example, if we take target as 30, here first element is 10. Compare 10 and target element. Here 10 is less than 30, so ignore. Next element is 20. 20 is less than 30. Ignore. Here next element is 20. 20 is less than 30. Ignore. Here next element is 30 and it is equal to target element that is 30. So this is our output. Here this is the first position where element is equal to target element. We need to find the position where element is equal to or greater than the target element. If our target is 35, then here 10 and 35, 10 is smaller, 20 and 35, 20 is smaller, 20 and 35, 20 is smaller, 30 and 35, 30 is smaller, here also same, here also same, here also same, here 40 and 35, here this element is greater than 35. So this is our output. This is the first position where element is greater than or equal to target element. Here in this example, element is greater than target element. So our aim is to find the first position where element is greater than or equal to target element. Simple, right? To solve this problem, we'll use binary search algorithm, but normal binary search doesn't work here. We need to modify the binary search algorithm. Here we have normal binary search algorithm. In this, first we'll start by defining a search space. That is, we'll take two pointers, low and high. Low will point to the first element of the list and high will point to the last element of the list. Low equal to 0, high equal to length of list minus 1. Then we'll find the middle element. For that we'll use low plus high truncated division 2 formula. Then we'll compare the middle element and the target element. Here there are three possibilities. One is mid element is equal to target element. In that case we'll return the index. And the second scenario is mid element is less than target element. If middle element is less than target element, then we need to search in the right side, right? So we'll take low equal to mid plus 1. Third scenario, mid element is greater than target element. In that case, we need to search in the left side. So high will point to mid minus 1. To change the search space, we'll use low and high pointers. This is the logic behind the normal binary search algorithm. Now, we need to use this binary search algorithm to find the lower bound. If I take target as 30 here, then this is low, this is high. So we'll find the middle element. So middle element is this and target is 30, right? When we compare target and middle element, here target is equal to middle element. In that case, in the normal binary search, we'll return its index, that is 3. So we'll get output as 3. But here, the first position where element is greater than or equal to target element is second position. So we need to get output as 2. But here, we'll get output as 3, right? That's why normal binary search doesn't work here. So what we need to do is, first we need to start by looking at the entire list. Take the entire list. Find the middle element of the list. If the middle element is smaller than the target, ignore left half and continue searching the right half. And if middle value is greater than or equal to the target, keep this position as possible answer and continue searching the left half. This process continues until there is only one possible position left, and that position is returned as lower bound, which is the index of the first number greater than or equal to target. Let's take examples. Okay, if target is 30 and this is a list, we want to find where we can place this 30 in this sorted list. Here output is in the fourth index, right? Here we can see 10, 20, 20, 20. These are all smaller number and here 30 is equal to 30. This is the first position where we can place our target. So output is index 4. In the lower bound, if target is already present in the given sorted list, we'll search for the first occurrence, okay? Okay, next let's apply modified binary search algorithm and see how this algorithm works to find lower bound index. Okay, so here we have list, target is 30. Initially low will point to the first index, and in normal binary search high will point to last value. But here high will point to length of list. That is, here we'll take low equal to 0, high as length of list, here 8. In normal binary search, we'll take high as length of list minus 1, that is the last index of the list. But here we need to take high is equal to length of list. Why? Because here we are finding the position to place the target element in the sorted list. That position can be at the beginning, between elements, or after the last element. For example, if target is 80 here, so we need to place 80 in the last index after this 50, because 80 is greater than all other elements here. So we need to place that at last. So to place that, we need this position, right? So that's why here we need to take high as length of list. Okay, next we need to find the middle element. Here low plus high truncated division 2 to find the middle. 0 plus 8 truncated division 2, so we'll get this as middle. Then compare this middle element with the target element. Here middle element is equal to target element. If the middle value is greater than or equal to the target, then we need to keep that position as possible answer, and we need to continue search in the left half. Here it is equal, so we need to continue search in the left half, and we need to take this position as possible answer. That's why we need to take high equal to mid. So now this is a search area. Now again find mid. 0 plus 4 truncated division 2, so we'll get this as middle element. Compare middle element with the target element. 20 is equal to 30. 20 is less than target here. When 20 is less than target, then we need to ignore left half. We need to search in the right half. So here low becomes this one, right? Low points to this one now, mid plus 1. So now this is a search area. So find the middle element. Here we'll get this as middle element. 3 plus 4 truncated division 2, so we'll get 3. Then compare this element with the target. 20 is equal to 30. No, it is not. 20 is not equal to 30. Actually 20 is less than 30. So we need to take low equal to mid plus 1. So now low will point to here. Now actually in this search area we have only one element, that is our possible answer. Here in the modified binary search, when low is equal to high, we need to stop the search. And here this is our possible answer. So here you can written low. Low will contain our possible answer. That is, output is 4th index. We can place target 30 in this 4th index without disturbing the sorting order. Let's take another example. Let's take 35. Here we can see 35 is not present in this list. So if you want to place 35, where will you place that? Here, right, in the index 6. So we'll get list as 10, 20, 20, 20, 30, 30, 35, 40, 50. So we need to get output as 6. Next, let's use modified binary search algorithm on this example, and we'll see whether we'll get right answer or not. So initially low will point to this, high will point to 8, length of list here. Then target is 35. Find the middle element. Low plus high truncated division 2, so we'll get 4. Compare 30 and 35. Here target is greater than middle element, so we need to ignore the left half and continue search in the right half. So to search in the right half, I need to take low as mid plus 1. Now this is our search area. Find the middle element. 5 plus 8, that is 13. 13 truncated division 2, so we'll get this as middle element. Compare 40 and 35. Middle element is greater than target here. So when middle element is greater than or equal to target, we need to take this as the possible answer, and we need to search in the left half, right? We need to take high equal to mid. Now this is our high. 30 and 40. Find the middle element. 5 plus 6 truncated division 2, so we'll get 5. This as the middle element. Compare 30 and 35. Middle element is smaller. When middle element is smaller, we need to search in the right half, right? So here low equal to mid plus 1. So now here you can see low is equal to high. Only one element is present here. So this is the possible answer. Written low now. Low value is 6. That is our answer. At 6th position, 6th index, you can place 35. Okay. Here in the normal binary search, we'll find the target value in the sorted list. Find the first position where value is greater than or equal to target. Return -1 if target doesn't exist. Works even if target is not present. If target is not present, then also we'll get an index. If duplicates present, returns any index of the target. Here, find first occurrence in case of duplicates. Here we'll take low equal to 0, high equal to length of list -1. Here low equal to 0, high equal to length of list. Because here we'll search for a target element. Here we are searching for the position. This is the stopping condition. When mid element is equal to target or low becomes greater than high, we need to stop normal binary search. But here when low becomes equal to high, we need to stop. Okay, so this is the difference between normal binary search and modified binary search. Next, let's write the program. Here input is a sorted list as well as a target element. So here we can see the code for that. Here I'll assume that you're already familiar with how binary search algorithm works. So I won't explain the terms related to binary search algorithm in more detail. So next, here let's define the function for modified binary search. I'll take lower bound. Here a list and target, just like we do in the normal binary search. Low equal to 0, 2 pointers, high equal to length of list. Then in the binary search, we'll use while loop and we'll take while low is less than or equal to high. But here we need to stop when low becomes equal to high. So when low is less than high, we'll perform these operations. When low becomes equal to high, we need to stop. Here find the middle, low plus high truncated division 2. Then we need to compare middle element. So numbers made is less than target. Look, if target is greater than the middle element, then we need to search in the right side, right? We need to take low equal to mid plus 1. This is how we will search in the binary search algorithm also, right? If target is greater than the middle element, we'll search in the right half. Else, if middle element is equal to target element or target is smaller than the middle element, then we need to search in the left half. Also, what we need to do is, we need to take the middle index as one of the possible answer. That's why here we need to take high is equal to mid. In the normal binary search, we'll take high is equal to mid -1. But here we need to include this target is equal to middle element condition also here in this else block. That's why we need to take high equal to mid. We need to take that index as one of the possible answer. Okay, so we need to take high equal to mid. Then here after while loop, when low becomes equal to high, we need to return low. Here you can return high also because this condition will stop when low is equal to high. So both low and high point to the same index. Here I'll return low. Now we are done. Here we need to call this function and store that result because this function will return a result, right? Next, print the result. Save and execute. Number of elements in the list. Let's enter 5. Then I'll enter 35. We can place this 35 after this 30, right? Before 40. So index is 0, 1, 2, 3. We need to get index as 3. Yes. I'll enter 40. So we'll get lower bound index as 3. Okay, so this is the one of the way to solve this problem. Next, let's talk about another method. That is the classic method where we'll store the index and we'll continue search in the left side. So start by defining your search space. Take low and high pointer. Low equal to 0, high equal to length of list -1. Then find the middle element. Low plus high truncated division 2. Use the same formula. Then compare middle element and target element. Here we need to consider only two possibilities. Because here we want to find the first position where element is greater than or equal to target element. So here we need to consider only two possibilities. Mid element is less than target and mid element is greater than or equal to target. So when mid element is less than target, if element is less than target, we need to ignore that, right? So here when middle element is less than target, we need to ignore the left side and we need to search in the right side. To search in the right side, we need to take low equal to mid +1. Why ignore all the elements in the left side of the middle element? That is because here numbers are sorted in ascending order. If middle element is less than target element, that means all the elements present in the left side is also smaller than the target element. So no need to check them. Simple, right? Next, let's consider next scenario. What if mid element is greater than or equal to target element? Here we want to find the position where element is greater than or equal to target element. When this condition is true, that means we found an element which is greater than or equal to target element. So now we found our answer. So what we can do is we can save that answer. Take a variable, for example answer, then store that index. Now we found our answer. We need to stop, right? No, because here we found a position where element is greater than or equal to target element. But here in the lower bound, we want to find the first position where element is greater than or equal to target element. Here we found a position where element is greater than or equal to target element. Whether this one is the first position, we don't know. So what we need to do is we need to continue search in the left side. To search in the left side, we need to take high equal to mid minus 1. When the middle element is greater than or equal to the target, we store the index because it satisfies the lower bound condition. A element greater than or equal to target element. So it can be one of the possible answer. However, we can't stop here. Binary search doesn't check elements sequentially. Even though we found a position where element is greater than or equal to target, we do not know whether this is the first such position. There might be another element on the left side that is also greater than or equal to target element. Here we need to find the first position where element is greater than or equal to target element, not any position where element is greater than or equal to target element. That's why when we found a position where element is greater than or equal to target element, save that answer. It can be one of the possible answer and search in the left side. Why left side? Because if I want to search for the first occurrence or first positions, we need to search in the left side because here numbers are sorted in ascending order. So this is the modified version of binary search algorithm to solve lower bound problem. In the previous part, we modified binary search algorithm to solve lower bound problem. We can call it as version 1 and this algorithm as version 2. What is the difference between previous version and this one? Okay, so in the first version, we can call it as boundary method. Instead of storing answer, we shrink the search space until low itself becomes the lower bound. But in the second version, we can call it as store answer method. Here, whenever we find a element which is greater than or equal to target element, we'll store that index as one of the possible answer and move left to check if there is an earlier valid position. First version, in the previous version, we won't take any variable to store the result, but here we'll use a variable to store the result. And in the previous version, initially we'll take high equal to length of list. Here we'll take high equal to length of list minus 1. That is because in the previous version, by setting high equal to length of list, we can handle the case where all elements greater than target element gracefully. But here, this version stores the possible answer in a separate variable. So high only needs to cover actual indices of the list. There is no need to go past the last element because answer handles the case when target element is greater than all other elements in the list. And also stopping condition is also different. Here in the first version, when we have only one element in the search space, we need to stop. But here when low becomes greater than high, we need to stop. This second version is more similar to normal binary search algorithm. Okay, so let's take few examples. First, let's take target as 20 and find the middle element. Here, this is the middle. Compare the middle element and target element. Here, middle element is greater than target element. When we found an element greater than or equal to target, what we need to do is we need to store this index. So take a variable and store this index and search in the left side. So here, high need to point to this side. We can ignore these elements now. This is a search space. Now find the middle element. This is middle element. Compare middle element and target element. Middle element is equal to target element. When element is greater than or equal to target element, save the index and search in the left side. So here answer becomes 1. High equal to mid minus 1. Calculate middle. So here 10 and 20. Here 10 is smaller. Here middle element is less than target element. When middle element is less than target element, we need to search in the right side. So low becomes mid plus 1. Now here you can see low is greater than high. In this binary search algorithm, when low becomes greater than high, we need to stop. So this is our answer. Here we need to find the first position where element is greater than or equal to target element. Here 20 is equal to 20 and it is present at index 1. That is our output. Okay, let me take another example. Let's take 50. Okay, so this is low and this is high. Here you can see 50 is greater than all the elements present in the list, right? Initially what we'll do is we'll take this answer as 8. That is length of list. Then find the middle element. 30 is equal to 50. No, 30 is smaller than 50. If element is less than the target element, search in the right side. Low becomes mid plus 1. This is our search area now. Find the middle element. Compare middle element and target. Here element is less than target element. So search in the right side. Now again find the middle element. Now find the middle element. 30 is less than 50. So search in the right side. Find the middle element. 40 is less than 50. So low becomes mid plus 1. Search in the right side. So now here you can see low is greater than high. So now we need to stop. So we'll return this answer as 8. As I said, in this version, to handle this scenario, when target is greater than all other elements in the list, we'll use this method. Here we use an answer variable to store the possible lower bound index at each step of binary search. We initialize this variable with the default value, that is length of list, because the lower bound represents an insertion position, not necessarily an existing index. If the target is greater than all the elements in the list, then middle element is less than target condition will be true for every mid. In that case, the condition middle element is greater than or equal to target never becomes true. So answer equal to mid is never executed. Without a default value, answer would remain undefined or incorrect. So by initializing answer equal to length of list, we correctly return the position after the last element, which is the valid lower bound. Here, if we didn't initialize answer as length of list, here we saw the statement answer equal to mid never executes. So we won't get proper answer. So that's why initially we need to assign length of list as the default value for this variable. Okay, next example. Target is 25. Initially we'll take this value as 8, that is length of list. Now find the middle element. Compare the middle element 30 and 25. Here 30 is greater than 25. Here we found a position where element is greater than target element. So it can be one of the possible answers. So save the index. Now answer becomes 3. We'll update this variable. Now answer is 3. We need to search in the left side. High is mid minus 1. This is our search area now. Find the middle element. Then compare 20 and 25. Here 20 is smaller. If element is smaller, then search in the right side. So low becomes mid plus 1. Now this is our search area. Find the middle element. Compare 20 and 25. 20 is smaller. So search in the right side. Low becomes mid plus 1. So now here you can see low is greater than high. We need to stop binary search. So this is our answer. Here at index 3, we have an element which is greater than 25 here. That is our target. Okay, next let's write the program. Here we have a normal binary search algorithm. Here you can see the program. Next, let's modify this algorithm. Low equal to 0, high equal to length of numbers minus 1. Low is less than or equal to high. Find middle. And if middle element is equal to target, here we have this condition. We don't want this. We can remove this. Here, if middle element is less than target element, if element is less than target element, then we need to ignore left side. We need to search in the right side. So low equal to mid plus 1. Else, this will execute only when numbers of mid is equal to target or numbers of mid, that is mid element is greater than target element. In this case, we need to store the mid element also. So we'll take answer equal to mid and initially I'll take its value as length of list. To find the length of list, we'll use len. If middle element is less than target element, then I'll take low equal to mid plus 1. Search in the right side. Else, When this else becomes true, when middle element is greater than target or when middle element is equal to target element. What we need to do at that time? We need to store that index first. It can be one of the possible answer. Then we need to search in the left side. Why left side? Because here we want first position where element is greater than or equal to target element. To search for that first position, we need to search in the left side. Next, here we need to return answer. Why answer? Because it will hold a final answer. Then here, this function will return answer. Then we can just print that without using if else. I'll print like this: lower bound index and result. Save and execute. Be careful about the indentation, okay? Let's enter 5. Lower bound index is at 2. Let me enter 30. So at index 3. If I enter 6, we'll get lower bound index as 5. Okay, so this is how we can solve the lower bound problem using binary search algorithm. Next, let's talk about upper bound problem. Here is the problem statement. Given a sorted list and a target value, find the index of the first element that is strictly greater than the target. Here input is a sorted list and a target element, and output is index of the first element that is strictly greater than the target. Here we have an example, sorted list and target element. Here output is 5. For example, if I take target as 30, then here output is 7th index. That is, when target is 30, we need to ignore all the numbers smaller than or equal to the target element. Here 10 is smaller than 30, 20 is smaller than 30, 30 is equal to 30. So we need to ignore all the numbers which are smaller than or equal to the target element. Then here 40 is greater than 30. This is the first position where element is strictly greater than the target element. So this is our output. If target is 25, here 10 is smaller than 25, 20 is smaller than 25, 30 is greater than 25. This is the first position in this sorted list where element is greater than the target element. So this is our upper bound index. To solve this problem, I'll use binary search algorithm, but here we'll modify the binary search algorithm. Start by looking at the entire list. Find the middle element of the list. If the middle element is less than or equal to the target, ignore left half and continue searching the right half. If the middle value is greater than the target, keep this position as possible answer and continue search in the left half. This process continues until there is only one possible position left. That position is returned as the upper bound, which is the index of the first number greater than the target. So we need to use this algorithm now. In the previous tutorial, we talked about lower bound problem. The difference between upper bound and lower bound is, in the upper bound, we'll find the first position where a number greater than the target can appear. Here, we'll find the first position where target can appear. Here you can see the difference between upper bound and lower bound with an example. Alright, next, let's take an example. Here we have a list. Target, let's take target as 30. Then in the binary search algorithm, we'll take 2 pointers, low and high. Low will point to the first element and high will point to the last element. But in the upper bound, high will point to length of list. That is, here we'll take low equal to 0, high as length of list. That is because here we are finding the position, right? If our target is 60, where you will place this 60 in this list? Here in the 8th position, right? Because 60 is greater than all these elements. What is the output when target is 60? That is 8th position. To get that, we need to take high as length of list. Both lower bound and upper bound are about finding a position. That position can be at the beginning, between elements, or after the last element. So algorithm must allow searching one position beyond the last index. That's why we'll take high as length of list here. Alright, next we need to find the middle element. So low plus high truncated division 2, we'll get here 4 as middle element. Formula is say mid equal to low plus high truncated division 2. 0 plus 8 truncated division 2, that is 4. So we'll get this as our middle element. Now we need to compare the middle element and target element. If middle value is less than or equal to the target element, then we need to ignore the left part and we need to search in the right part. Here middle element is equal to target element here. So we need to search in the right side. Low becomes mid plus 1. So now this is our search area. Find the middle element. 5 plus 8, that is 13. 13 by 2. So this is our middle element. Compare the middle element with the target element. 40 is equal to 30. Here 40, that is middle element, is greater than 30. When middle element is greater than 30, what we need to do is we need to keep this position as well as we need to search in the left side. So we'll take high equal to mid. So this will become my high now. Now this is our search area. Find the middle element. 5 plus 6 truncated division 2. 5. Compare the middle element and target element. Here middle element is equal to target element. When middle element is less than or equal to target element, we need to ignore the left part and we need to search in the right side, right? So here low becomes mid plus 1. Now low will point to here. According to the algorithm, when we have only one element, that is when low becomes equal to high, we need to stop the search. So here this remaining position 6 is our output. We can place this 30 in the sorted list at index 6. So you can see the difference between lower bound and upper bound here. According to the lower bound, we can place our target 30 here in the 4th index. But here in the upper bound, the output is at index 6. Now let's take another example. Let's take 35 as our target. Compare middle element and target element. Here target is greater than the middle element. Middle element is less than the target element. When middle element is less than or equal to target element, we need to search in the right side, right? So low becomes mid plus 1 here. Okay, this is our search area. So again find the middle. Compare the middle element and target. Here middle element is greater than the target. Middle value is greater than the target, then we need to keep that position and we need to search in the left side. Here, so mid becomes high. Now again find the middle. This is middle. Compare middle and target. Here middle element is less than target element. When middle element is less than target element, so we need to search in the right side, right? So low becomes mid plus 1. Now only one element is present here. Low is equal to high. Now we need to stop and output is 6th index. We can place 35 in the 6th index. Let's take 5 as our target. Compare 30 and 5. Here target is smaller, middle element is greater. Keep this position and search in the left side. So this becomes high. This is our search area now. Find the middle element. 4 truncated division 2. So this is middle. Compare middle and target. Here 20 is greater. When 20 is greater, keep this position and search in the left side. This becomes high now. Now again find the middle element. 20 and 5. Here middle element is greater than target now. So when middle element is greater than target, keep that position and search in the left side. Calculate middle. This is middle. 10 and 5. Again 10 is greater than 5. When 10 is greater than 5, we need to take middle as high and we need to search in the left side, right? Now low is equal to high. We need to stop and this index is our output. So you can written low. So 0th index. You can place target 5 at 0th index. Okay, next let's write the program. Here we have a lower bound program. I'll give you the link of this video in the description box. Today let's write upper bound program. Input is same, a sorted list and a target element. Here let's define upper bound function. So function name is upper bound, numbers and target, then low equal to 0, high equal to length of numbers. While loop condition, low is less than high. When low becomes equal to high, we need to stop. Inside the loop, mid, low plus high truncated division 2. Here, when middle element is less than or equal to target. In the upper bound, when middle element is less than or equal to target, we need to ignore the left side and we need to search in the right side. That's why we need to include this condition here. Low is equal to mid plus 1. That is, we need to search in the right side. Here else, high equal to mid. When middle element is greater than the target element, we need to take that position as possible answer and we need to search in the left side. That's why I need to take high equal to mid. In the lower bound, we'll use less than symbol. Here in the upper bound, here you need to use less than or equal to. That is the difference. Then here you need to return low. Low becomes equal to high. This condition becomes false, so control will come here. Low and high both points to the answer. You can take written low or written high. I'll take written low. Alright. Then here we need to call this function upper bound. And here we need to print upper bound index. And we are done. Let's save this and execute this. Let's enter target element as 30. In the lower bound, we'll get index as 2, but here we'll get index as 3. Okay, so this is the first way to solve this problem. We can solve this using another method. This method is more simpler and more similar to normal binary search algorithm. Here we want to find the first position where element is strictly greater than the target element. For that, what we need to do is, first step, start by defining your search space. So we'll take low equal to 0, high equal to length of list minus 1. That is, we'll point low to the first element and high to the last element of the list. Same as normal binary search. Then we'll find the middle element. We'll use the same formula, low plus high truncated division 2. Then we'll compare the middle element and target element. Here we need to consider only two possibilities. One is when element is smaller than or equal to the target element. Another one is when element is greater than target element. Here, if elements are smaller than or equal to the target element, we need to ignore them, right? Here we want to find the first position where element is greater than the target element. So, the elements which are smaller than or equal to the target elements are ignored here. If middle element is less than or equal to target element, that means all the elements present in the left side of the middle element is also less than or equal to the target element. Because here input is a sorted list. We are using list where numbers are sorted in ascending order. So here we need to ignore all the smaller number or numbers equal to the target element. So that's why when middle element is less than or equal to target element, we need to search in the right side. For that, we need to take pointer low equal to mid plus 1. If middle element is less than or equal to target element, just ignore them. So search in the right side. Okay, so the next case is when middle element is greater than target element. So what we need to do when middle element is greater than target element? Here our aim is to find the element which are strictly greater than the target element, right? Here we found an element which is greater than target element. So it can be one of our possible answer. Why it is one of the possible answer? Because here we are not searching the elements in the sequential order. We are using binary search algorithm. Because of that, we don't know this element is the very first element where element is greater than the target element. Here we got a position where element is greater than the target element. Whether this one is the first position, we don't know. In the upper bound problem, we want to find the first position where element is greater than the target element. So to find that, we need to continue search in the left side. Why left side? That is because if I want first position or first occurrence, we need to search in the left side in the sorted list. Okay. So here first take a variable and store this index. Index is here mid. Okay. Continue search in the left side. So for that you need to take high equal to mid minus 1. Why save the index? Because here we found an element which is greater than the target element. So it can be one of the possible answer. Then why search in the left side? Because we found an element which is greater than the target element, but we don't know that is the first element in the list where element is greater than the target element. Here we want first position where element is greater than the target element. To find that first position, we need to continue search in the left side. Let's take an example. Let's take target as 25. First, let's define the search space low and high. Then find the middle element. So here this is mid index, that is 3, and this is middle element. Now compare the middle element and target element. Here element is greater than the target element. Now we found an element which is greater than the target element. Now what we need to do? This index can be one of the possible answer, right? Because here element is greater than the target element. So I'll store that index. Take a variable and store that index. Now next, we need to continue search in the left side. Here, now high equal to mid minus 1. This is our high. This is our search area now. Then again apply modified binary search algorithm. Here low plus high truncated division 2. So this is our mid. Compare mid and target element. Here element is less than the target element. When element is less than target element, we need to ignore that element. So we need to search in the right side of the middle element. So low equal to mid plus 1. So now this is our search area. Find the middle element. Low plus high truncated division 2. So we'll get this. Compare 20 and 25. Here 20 is smaller than the 25. So what we need to do? We need to search in the right side of the middle element. Low becomes mid plus 1. Now here you can see low is greater than high. In the binary search algorithm, when low is greater than high, we need to stop. So we got answer as 3. Let me take 15. This is low, this is high. Find the middle element. Compare the middle element and target. Here this element is greater than the target element, one of the possible answers. So store the index. Then search in the left side. Find the middle element. 20 and 15. 20 is greater than 15 now. This can be the first position where element is strictly greater than the target element. So store this index now. We don't want previous index. Store this latest index now. Answer is 1. And continue search in the left side. So here this becomes high. Again find the middle element. 10 and 15. Here 10 is smaller. Element is smaller, so search in the right side. Low is mid plus 1. Now here low is greater than high. When low is greater than high, we need to stop. This is our answer. Let's take target as 30. This is mid. Compare middle element and target element. It is equal. When element is smaller than or equal to middle element, we need to ignore left side and we need to search in the right side. So here low becomes mid plus 1. So now this is our search area. Find the middle element. This is middle element, right? 30 and 30 equal. So search in the right side. Now find the middle element. 30 and 30 equal. So search in the right side. Low equal to mid plus 1. Find middle element. 40 is greater than 30. So we need to take this as one of the possible answer. So store that index and search in the left side. To search in the left side, we need to take high equal to mid minus 1. So now here you can see low is greater than high. We need to stop. This is our answer. Now what about target as 50, which is greater than all the elements in this list? Here mid element and target element. Middle element is smaller. So search in the right side. Middle element and target element. Here middle element is smaller. So search in the right side. Again find the middle element and target. Here element is smaller than the target, so search in the right side. Again middle element and target. Here target is greater, so search in the right side. So here low equal to mid plus 1. Now here you can see low is greater than high. What to do in this situation? Here whenever middle element becomes greater than the target element, we'll store that index in a variable, right? So initially I'll take its value as length of list. Default value for this variable is length of list. So here in this situation you can see in every comparison element is smaller than the target element. So answer equal to mid is never executed. That's why we'll take default value for this variable, that is length of list. Here length of list is 8. So we'll get 8 in this situation. So upper bound index for target 50 in this list is 8th index. To solve this scenario gracefully, we'll take default value for this variable as length of list. If we found a position where element is strictly greater than the target element, then we'll replace this value. We'll upgrade this value. So this is about example. Next, let's write the program. Okay, here we have a lower bound program. Now we want to write upper bound program. I'll keep the function name as binary search. You can take upper bound also. Low equal to 0, high equal to length of numbers minus 1. This is the 2 pointers to define search space. Next here we'll take a variable to save the index of the element when element is strictly greater than the target element. Initially I'll take its value as length of numbers. Then low is less than or equal to high. This is the loop condition for normal binary search. Then find the middle element. Then compare numbers of mid is less than or equal to target element. If middle element is less than or equal to target element, ignore those element, search in the right side, that's why low equal to mid plus 1. Else. Here else part will execute when middle element is strictly greater than the target element. That time what we need to do? We need to save that index and we need to search in the left side. And lastly we need to return answer. Okay, next here inputs, target, and we need to call the binary search. It is for upper bound. Here we need to take a variable to store the result, and here we need to print upper bound index. Save and execute. Let's take 5 elements, numbers in ascending order. Let's enter 60. So 5. Enter 6. Let's enter 2. Index 3. Okay. So this is how we can solve upper bound problem using another method. Okay, so this is how we can solve lower bound and upper bound problems. Next, using this lower bound index and upper bound index, we can calculate the count of occurrences. That is, counting the number of occurrences of a number in a sorted list. So example, in this list, if I take target as 30, it appears 4 times. If I take target as 20, it appears only once. If I take target as 10, it appears only once. Okay, so how to find count of occurrence using lower bound and upper bound index? Here we need to find the upper bound index of target. So here target is 30. Upper bound index of 30 is 6. Then here lower bound index, that is 2. Then we need to use the formula count is equal to upper bound minus lower bound. So 6 minus 2, that is 4 times. Okay, here upper bound index is the first position where element is strictly greater than the target element. In this example, 10, 20, 30 are less than or equal to target element. That's why the 6th index is the upper bound index here. For the lower bound, we need to find the first position where element is greater than or equal to the target element. Here at index 2, 30 is equal to 30. So that is the first position. So lower bound index is 2. 6 minus 2 will get 4. Correct, right? Count is 4. So now here you can see another example. If we take target as 20, here to find the count of 20, we need to find upper bound index and lower bound index of 20. Here upper bound is index 4. This is the position where element is strictly greater than the target element. Then here lower bound index, we need to find the first position where element is greater than or equal to the target element. Here this is the first position, right? Here element is equal to target element. So 1. Now 4 minus 1 will get count, that is 3. So 20 appears 3 times in this example. If target is 30, upper bound is 6 and lower bound is 4. So 6 minus 4, 2. 30 appears 2 times. Okay, now why this lower bound and upper bound works? That is because here list is sorted. When list is sorted, all the duplicate appears together next to each other, right? So by finding upper bound and lower bound, we can calculate count easily. Upper bound is the first index greater than the target element, and lower bound is the first index of the target element. So when we minus lower bound from the upper bound, we'll get the count. And also if an element is not present, for example, if I take target as 50 here, I want to find the count of occurrence of 50, then here you can see upper bound is 7th index, lower bound is also 7th index, 7 minus 7, 0. So we'll get count as 0. To find the count, we need to first find the upper bound index and lower bound index of the target element. Then by using the formula upper bound minus lower bound, we can calculate the count easily. Alright, next let's write the program. Okay, so here we have upper bound program. Okay, first let's define two functions. One is for lower bound, another one is for upper bound. We'll calculate upper bound and lower bound. Then using the formula upper bound minus lower bound, will calculate the count. So here this is upper bound. So upper, let's take function name like this. Okay. So here you can see the condition less than or equal to the target, then low equal to mid plus 1. This is upper bound program. Before that, let's define a function for lower bound. Take function name as lower bound, and here difference is only this symbol. If middle element is less than target element, search in the right side. Otherwise, save the index and search in the left side. This is lower bound. Here in the upper bound, when middle element is less than or equal to the target element, search in the right side. Otherwise, save the index and search in the left side. Right? Next, we need to call upper bound and lower bound function. So here, upper index as the variable name. You can take any variable name. Okay, suitable variable name. Here, upper bound. Let's call upper bound function first. Then calculate lower index, that is lower bound index. I'll call lower bound function name. Here you can see lower bound and upper bound. We'll call these two functions to find upper bound and lower bound of the target element. Next, here we need to use the formula count is equal to upper bound minus lower bound, upper index minus lower index here. Done. Then we need to print that, and we are done. Let's save this and execute this. Let's enter 5 elements. 1, 2, 2, 3, 4. Let's enter 2. So count of 2 is 2. It appears 2 times. Let's enter an element which is not present in the given list of numbers. So count is 0. So let's take 40. 40 appears 1 time. Okay, so this is how we can find the count of occurrence of the target element using upper bound index and lower bound index of that target element. So that's it for now, guys. Thank you for watching. Don't forget to subscribe to my channel. I will meet you in next class. Till then, take care.